Welcome back, everybody. Today I want to just kind of discuss some general details of hypothesis testing, clear up any misconceptions before we move forward with too many examples. We'll spend a couple weeks on this stuff. And then even after we come back from break, we're going to be putting all this together in kind of a model selection format where you're going to be doing something called the stochastic search variable selection. It's basically everything you learned using this stuff, the Bayesian way of doing things, in an MCMC format. So there's an MCMC that can kind of march through model spaces and then select a model for you. Of course, a lot of the discussion is what priors are you using and why, and what are the properties of those priors. And then I think to do everything justice, we should compare to non-Bayesian devices or pseudo-Bayesian devices or things that Bayesians use and other people use and they describe as non-Bayesian things, but we describe as Bayesian things. So lots to clear up here. And then probably I should tell you what I actually do at some point. I don't think I want to corrupt you too soon. So, model selection, or hypothesis testing, if you will. So we'll just frame it in that light. We did look at a kind of a model selection problem with an intercept and a slope, and then we did hypothesis testing on the intercept. That's what I mean by model selection. So intercept in or out of the model. Hopefully you kind of recognize that is just kind of a sharp hypothesis test. So where alpha could have been 0 or could have been something else. So all the properties about that and the typical sort of hypothesis testing problem are exactly the same. Okay, so two things that we've looked at so far are the Bayes factors and the max likelihood ratio test. So you might consider this right here an approximation for that. And we talked about that last time. And so what is the Bayes factor? If I really just write this out, it's just f of x, the data, that's all of your data. So this is your joint model, conditioned on h naught divided by f of x, conditioned on the alternative hypothesis, where I've integrated against some priors that are weighting how much I value thetas in the null space versus the alternative space. This is true in general, regardless of which type of hypothesis test that we're doing. We've kind of talked about these priors and had some indication that we have to be really careful about whether or not they're proper or non-proper. So I'll give you just a quick hint. If both parameters are in both of the models, like the intercept, or not the intercept, the slope in that other regression problem, then we can put improper priors on. So any proportionality constant that we introduce on those will cancel each other out in this ratio. And the easy way to think about that is if all of a sudden you introduce an arbitrary integrating constant or something like that, you're using a flat prior, and you introduce some arbitrary number to represent proportionality, like 1, that's as arbitrary as 10.5 or a million. If those numbers don't cancel out in the numerator and the denominator, you should not be using it. Okay, so if there's some arbitrariness, don't use an improper prior, use a proper prior. Just bear in mind, when we calculated a posterior probability, we had something like this. The likelihood times the prior, and then we divide it by the integral of that thing. Pi theta d theta. And I'm going to integrate over the entire range of theta. Theta in all of theta's range. So we might represent it like that. So negative infinity to infinity, you might think. So if I have an arbitrary proportionality constant here, if I'm trying to put a flat prior on something, and I let that be 1 here, we would also pick a 1 there, and they would cancel each other out. If I arbitrarily chose the number 10 right here to represent some flat prior, it would also cancel itself out. So it wouldn't matter which number that we picked right there. Saying that, if I were looking at a Bayes factor and Whatever I place flat mass on doesn't appear in the numerator and the denominator, you have no business doing that. And in fact, it's totally wrong. So early, I would say like late 90s, early 2000 hypothesis testing papers. If you want some good comic relief, go through the ones that are selecting models, and you'll see this error made quite often. So totally arbitrary stuff being introduced into the literature. Does that kind of make sense? So as an example, we looked at intercept and slope. So if I were picking the slope, if I were trying to do a test like this, where I had some model, yi is equal to alpha plus beta xi, in my null space, my null hypothesis, again, was alpha is equal to 0 versus alpha is something other than 0, I still need to deal with beta in everything. So if I'm trying to come up the marginal probability of my data, so that would be in terms of y's given the xi's, I'd need a prior on beta and alpha. So this is a parameter that doesn't appear in both the numerator and the denominator. So if I put a prior on alpha, and I used a flat prior in the alternative range, it wouldn't cancel in both the numerator and the denominator. So we talked about that example last time. Saying that, since beta isn't part of my hypothesis space, if I were going to integrate that out and get the marginal probabilities of the data under the null and the alternative, since the test isn't concerning ourselves with beta, if I used a flat prior on beta in the numerator and the denominator, all the arbitrariness would cancel out. That's what most people would probably do. So, quick rule of thumb, if you're introducing arbitrariness, arbitrary integrating constants, anything like that, they better cancel out of the numerator and the denominator. Same is true for your likelihood functions. So if I have likelihood here, if I multiply the numerator by c and the denominator by c, they just cancel out. So I never even think about the normalizing constant when I'm doing inference and constructing a posterior, because any arbitrary constants cancel. So be aware of that up front. You have to put some thought into these priors. We'll look at a lot of examples as we go through these different cases for testing. The max likelihood ratio test is kind of like this. It's kind of like the marginal, something about the margin of the data, but we're conditioning on thetas. So Bayes factor, what do? We integrate across theta, and something you might have been familiar with already is the maximum likelihood ratio test statistic, and you're just maximizing over thetas. So in cases where the distribution's on theta, i.e. the likelihood, so let me rephrase that, not the distribution, the likelihood, when it's very peaky and I'm integrating over it, it's very similar to maximizing over it. Okay? So think about like a rectangle or something like that. So integrating over it, its area is very similar to the height. So as the width starts getting narrower and narrower, they agree with each other on the same things. Okay. This classicist is used for totally different reasons than Bayesians. So what they're usually doing is they're usually coming up with a test where they threshold this thing. So these are the same things. I'm just taking the sampling distribution, and then I'm thinking about this as a function over theta. I've operated on theta, but I use this description, f, the sampling distribution, but it's more correct to talk about it as a likelihood function because I'm operating on theta. What does the equation look like? They look the same up to proportionality. They're coming in the form of a ratio, so any proportionality constants cancel each other. So let me give you a hint. If you're ever using a likelihood and it's supposed to mean something to you, you've used it in a ratio sense. So if somebody says the likelihood of something is 0.8, they've told you nothing. So they're mincing their terminology. You'll hear it on television shows. But the likelihood is 0.99, it's supposed to happen. You're talking about probabilities, which are different. Okay, so likelihoods always come in through ratios. You might be familiar with log likelihoods, and they'll come in through differences, but that's the same thing. Okay. Let me just make a comment. P-values are not measures of H0. This is a common misconception. So sometimes think big P and little p, they have differing amounts of information just on their own. If you tell me something has a p-value of 0.04 and you tell me something else has a p-value of 0.4, you might think that the p-value of 0.04 is more compelling against the null hypothesis. That is not true. That's false. So in some cases it might be true. But in general, it's not true. It's a function of n, and it's a function of the type of hypothesis that you're testing in the first place. So we'll look at an example of that. So let me just ask you a quick question. Two scientists have two different p-values. One's 0.04 and one's 0.1. Who has more evidence against the null hypothesis?
Is it neither?
It's not, oh, you don't know yet. So it depends until I tell you some more stuff. Let's consider the sharp test just for a minute. So this thing that they've inundated you with in Stat 101 classes. So just report the p-value, see if it ducks alpha. So if I have two p-values, and let's say, let's just rephrase the question just a little bit. Let's say experimenter 1 has a p-value of 0.04. It's like, wow, cool, we can publish. So an experimenter 2 has a p-value of 0.04. This person observed n is equal to 31 data points. So enough. Again, this is all supposed to be a little bit facetious. And this person right here, this has 1,000 data points. Who has more evidence against their null hypothesis? It's more of a question of how fast you got there. So what was the rate of decay of the p-value? Now, if the null is true, both of these are random variable. These are just uniform 0-1s. And they both have exactly the same information if the null were true. But in the alternative case, it's more of a decay rate of the p-value. And we'll talk about this a little bit more as we continue. But it's more of a question of how fast you got there. So this experimenter saw 0.04 and 31 data points. They got there quicker. So we're talking about the sharp test in this. Took the other person 1,000 data points to get down to that small p-value. And so experimenter 1, if they were testing the same thing, what parameter they were testing was exactly, had the same meaning, experimenter 1 has more evidence. So you should always ask the question when somebody's doing the sharp test, if you want to think like a Bayesian, you probably need to calibrate it to n. So what's n? And so if somebody told me they had a p-value of 0.06 and only 10 data points, I'd probably think whatever your hypothesis was or whatever your model was is probably not true. So 10 data points was able to come up with some evidence to reject that. So, but if somebody told me they had a p-value of 0.0499999, so really close to 0.05, but they're willing to reject it under the Neyman Pearsonian thing. So they have an alpha level of 0.05, so their type 1 error rate is 0.05. If they told me they had 1,000,000 data points, I'd think, I bet your null hypothesis is pretty close to being true. So they would say, well, it's different. And I would say, well, I could have told you that up front. So whatever you hypothesized about is not true. So, okay. So your null isn't true, but it's very close to being true. So we get into all of this conversation about practical significance and statistical significance, and it's really embarrassing. So if statistical significance wasn't practical to begin with, what are we doing? So you can think about all these things. Okay, so max likelihood ratio test is very similar to a Bayes factor, but the way they use them is different. So I'll just tell you, if you want to know more about this, I teach this in my inference class. So I teach that in spring. What people do is they'll come up with some sort of a threshold on that. By defining K, you define the type 1 error rate, and Neyman and Pearson have proven that by using this ratio, you minimize the type 2 error. So if you fail to reject and the null is true, that's a type 1 error. So and the type 2 error is if the null wasn't true and you accepted the null. So you'd make another type of error. So there's 2 errors you can make in any decision. Either say something is right and it's not, or you do the other thing on the other side of the hypothesis. I wonder if I could have said that any more confusing. So, but it is like that. Okay, so p-values themselves are not measures of the null hypothesis. So let me tell you about that. Let me just kind of demonstrate this is true. I want to point out every Bayesian calculation, and we can figure this out. I need to tell you a little bit more about this formula. We'll derive this in a couple minutes. Bayes factor inverse. There's a 1-to-1 relationship between the Bayes factor and the posterior probability of the null hypothesis. Probabilities are measures on something. So as that measure gets closer to 1, the more we believe that that's going to happen. As it gets closer to 0, the more we don't believe it. So what is a measure? So we know what this word means. If somebody said to you, you're going to go measure something, what are you going to do? If I tell you to go measure something, what are you going to do? What's that?
Like some numerical.
Yeah, some numerical, but you're going to get a measuring stick, right? You're going to get like a ruler or a tape measure or something like that. So, and that tape measure has the property that if things are bigger, then the measurement is bigger. The number is bigger. If things are smaller, then the measurement is smaller. That's called coherency. Okay, so as things get bigger, more true, then the measure should go up. As things get smaller and they're less true, the measure should go down. That's what a Bayesian is trying to tell you with their posterior probability. They're also calibrating it to the alternative. It has a particular property. So for a posterior probability, 1 minus the probability of the null is equal to the probability of the alternative. So I'm considering a space with just 2 hypotheses. And if you want to break this up into a space with lots of hypotheses, you would test one against everything else. So that would still be that same logical paradigm. So measures have this property too. So i.e., the probability of the null and the probability of the alternative add to 1. P-values don't do that. So let me give you an example. We'll come back and we'll prove that in a couple minutes. Let's try to get our footing and think about p-values just for a second. Okay, so when we're going to test something like this, so I'm going to say I have some x's out of a normal distribution. I'll call this mean theta, variance sigma squared. This thing right here. So this is just supposed to be stat 101. This is all IID stuff. I observe n data points from this distribution. So I have a histogram representation of that distribution, and I'm going to use that representation to say something about theta. Now, personally, this one-dimensional thing, I don't think we should be teaching hypothesis testing, and the only reason I'm doing it is because everybody out there is doing it. So we have to understand what it all means. That's the point of this whole sequence of lectures. You can decide what to do after. I think you should just estimate theta in this case. So it's kind of really weird that you would want to test something like this. H naught. Theta is equal to theta naught versus theta is different than theta naught. So we obviously do not mean is theta really theta naught, and this is a continuum. We mean, is it close? And I think everybody means that. So saying that, that classicist is really testing this thing. So they really are testing, is theta theta naught? And they're calibrating an error rate. So if you repeat their paradigm over and over and over again, if everything is normally distributed, and I come up with an alpha level, let's say it's 0.05, this is the error rate, and I get a p-value that ducks that thing so it's smaller for this problem. So let's say this number is 0.032, so reject. So if it's smaller, then we reject. The language is that you never accept anything, you can only falsify, and that's just because you can never know what's true, you can only know things that aren't true. So you can set up contradictory schemes. That we owe to Karl Popper. So thank you for that discovery. I probably could have figured that out by myself. So that's true. That is something you can bank on being true. That's about it. You can never know the truth. You can only say we falsify things. That's the concept of the black swan. If you've ever read that book. So just because I go out to the duck pond over here and I don't see any black swans, but I see white ones, it doesn't mean that there's no black swans out there. It just means I haven't seen one yet. So if somebody says there's no such thing as a black swan, I can falsify that by finding a black swan. So you're incorrect. But I can't do that by not observing a black swan. So that's the idea. So this is a typical name of the game, what they'll teach in most elementary stats courses. So they'll do something like this. What does this p-value actually mean? So let's say this is 0.032. What does it mean?
Under the null hypothesis, the probability of viewing the data point having some extreme.
Yeah, it's the more extremity of the data point. So that's the probability of your data and more extreme data. So what you actually do is you build up your test statistic. So what would your test statistic be that you would normally come up with here? If you wanted to be most powerful. Again, this is all just review. What test stat would you use? X bar n minus theta naught divided by sigma over root n. So this is what it would be. Where do we come up with x bar for measuring this thing? So x bar right here, this is just sum of the xi's divided by n. I goes from 1 to n. And I put an n on there because we're going to look at this test statistic in a minute, and I want you to remember it's a function of n. Where do we come up with this test stat? So what we usually end up doing is we threshold this thing. What do you usually threshold it to at to get the 0.05 level? This is like one of those things you remember from your table. 196. So that's the 2 standard deviations thing. 1.96. This is going to lead to this is going to be the critical threshold right here. So if this is less than 196, that's equivalent to this sort of thing. I don't know exactly what number that is, but I'm saying that the p-value itself would be less than alpha. Where did we come up with this test stat? Why that test stat? Why not like x bar over theta naught? So I could do something like that, right? I could say x bar n over theta naught, and I could say something about it. Basically, forget about that for a second. We're basically checking to see if this thing is close to 0. So is x bar close to theta naught? We know something about x bar. It converges to the truth. So it converges to truth theta. And we're asking, is truth theta theta naught? And so we're asking, is this thing big? So big values of this test stat will lead to rejection. So if we're asking is x bar close to theta naught, we might check to see if this thing is close to 1. Very similar, right? So we could have done that. Why do we prefer this one? Where does that come from? Instead of they just told me to do it. We know the distribution, so we presume that up front. So as soon as we add this, we could still come up with either one of them, though. So why did we choose this test stat? A lot of people call this like your z-score. I'll put an n on there again, just to let you know it's a function of n. So the z-score, typical sort of thing. Anybody remember? Anybody know, could come up with an answer why you've never done a test like this? The wheels turn for a second. There's some people in here that should know the answer to this. What do you think? You're right on the cusp.
It's the most powerful one.
It's the most powerful thing. So if you did go through the likelihood ratio test statistic, I'm not going to do this here because this isn't a class on full-blown inference and everything. If you did go through the max likelihood ratio test statistic, so if you looked over max, theta element of your null space, max, theta an element of H alternative, and I plugged in my likelihood function. So what's my likelihood function for the whole problem? It looks like this. E to the minus 1/2 x bar minus theta naught, or theta squared over sigma squared over n. This is equivalent to taking the product over all the little normal distributions. They look the same in terms of theta, that function. It doesn't look the same in terms of sigma. That's why it's a little bit different. But this would be the distribution you'd probably work with. You could have used the producted form and come up with the same thing. 1 over 2 pi. Sigma over root n. That's all known stuff. E to the minus 1/2 x bar minus theta squared, sigma squared over n. What's the maximum over the null space? Theta naught. There's only one value in all of the null space. It's theta naught. That's pretty easy. If I would have integrated it over everything, it would have been the same. That's the maximizing versus integrating. So the numerator is the same. The denominator changes compared to the base factor. What's the maximum likelihood estimator? If I took the log of this thing, took a derivative, set it equal to 0, and I solved for theta, it's x bar. So the maximum likelihood estimator is x bar. So this would be x bar. Right there. This is pretty easy to work with. So that cancels. This I can evaluate real quickly. It looks like 1. So I'm going to just get rid of it. So that canceled that. And I'm left with this thing right here. If I were to threshold everything, so if I said this was less than or equal to k, I have this thing right here is less than or equal to k. That is equivalent to this thing being less than or equal to some other number k. That k and this k are different numbers. So you'll notice that this thing right here is just the square of that. This is already positive, so I could have squared it and squared whatever that number was. And then I've got some monotonic stuff I've done to the function. So I could do that monotonic thing. And so there's some number here that corresponds to this number over here. And I can set that up on a probability scale since this is a random variable. And I can turn this into another equivalent calculation that looks something like that right here. This is a random variable and there's some probability distribution for x bar. And so I can go from this to thinking about that, and I can derive that test stat right there. You'll see that test stat right up here. This is z squared. So it's positive already. I've taken the absolute value. So squaring it, it's still 1 to 1. And taking the exponential or the log going the other way, those are all monotonic transforms. So it's just a different number that appears right here. How do you pick the number to threshold everything? You do it on a probability scale. So you map everything over to this. So real quickly, what is the distribution of z squared, or zn? So dist, let's just say z minus, or I'll say this. Let's not do the absolute value. How is this thing distributed? Normally distributed. Why is that true? You don't even need that in this problem. So CLT not required. But if I was having something come from a different distribution, then as n got high, this thing might be normally distributed or very close to a normal distribution that I might use it that way. So this is normally distributed. How's this thing distributed? Just the numerator. Still normal. Which normal? Where's it centered? It depends, right? If the null were true, so if h naught were true, it's 0. If h naught is true. So if this thing were centered at theta naught, x bar were centered at theta naught, subtracting off theta naught would center it at 0. If the alternative is true, it's centered somewhere else. So those of you familiar with the power calculation, you would work through that and figure out that thing. So everything, how is x bar scaled? What's its variance? Sigma squared over n. So if I divide by the square root of that thing, then I make this thing 1. So that's normal 0, 1. Why did we choose that test statistic out of all the other ones out there? This is also normally distributed. It's something different because I'm using theta naught to rescale it. It already doesn't make sense because theta naught is a shift parameter, not a scaling parameter. And if you go back to the Neyman Pearsonian thing, it's not a uniformly most powerful test statistic. And so you want to use the test statistic that has the most information. Now, those of you that think I'm anti-Neyman Pearson, actually really like that they showed us that. Which test statistic would I build my model out of? If I'm testing something or doing model selection, I would use Neyman Pearson's setup and say, these are the test statistics that I would use, but I'm going to operate in a Bayesian manner. So I think there's still some validity there. I think that's the most important thing that Neyman and Pearson showed us. So, by the way, Neyman and Pearson never did this. We just talked about it, doing it and what it would mean. So they were trying to help out Fisher. Backfired. Okay, so this whole test statistic under the null is normal 0, 1. So we're checking to see if it's close to 0. So in the typical sort of classical Stat 101 hypothesis test, you look at this normal 0, 1 distribution. So that's a normal 0, 1. This is the null distribution. So under the null hypothesis, our test statistic is distributed this way. So i.e. Zn is distributed this way. And take the absolute value sign so that I don't have to check if it's bigger than negative 1.96 or less than 1.96. So if I just drop the absolute value sign right here, I can go negative or positive. So let's just call Zn for a minute this thing. I always do this just so I can threshold it from one side and say 1.96. If I take the absolute value, then I don't have to say it's bigger than negative 1.96. So this distribution, x bar, is distributed like that under the null hypothesis. We all agree on the variance in the model because it was given and known. We're not sure about the centering of it. So we check to see how big this number is. So if it's way out here in the tails, it's probably not centered around theta naught. That's the idea. And I think that makes sense. It's just a question of what do the numbers actually mean? Are we interpreting everything right? So does anybody know what number you pick? So let's say this is 1.96 and this is negative 1.96. Does anybody know how much tail probability is right there on a normal distribution? Everybody should know this. This is the Stat 101 table thing that they would give everybody. What's the number? 0.025. And this is 0.025 based off of symmetry. And so what we're checking to see is we're looking to see if that test statistic is in this area that has 95% of the mass, which is 1 minus that, 0.025. And we're distributing that threshold over on the left and the right-hand side because this test statistic can take on positive or negative values. So we're basically checking to see how far away this thing is from 0. That's what they teach you in a Stat 101 class. And we go, well, that kind of makes sense. And they might teach it to you not through the formal Neyman Pearson thing in error calibration, but they say, well, if it's extremely different from 0, then probably the null hypothesis isn't true. And I agree with you. I just don't agree with what you might mean by that. And we might disagree on our thresholds. So how far away from 0 this test statistic would need to be before I considered it strong evidence against the null. Okay, so that's the basic p-value thing. So that's what we compute here for testing everything. So we compute this z-score right here, and I would essentially check to see if this was less than 1.96. And if I rejected this, I'd be wrong presumably 5% of the time, is the idea. So here's again the idea. I collect some data, n data points. I can get my x's. I hypothesize about theta. I build this test statistic and I check to see if it's the positive values thresholded by 1.96. If I did that over and over and over again, so I reject the ones that are less than 1.96, that would be equivalent to finding the p-value for this test statistic. What would the p-value be? It would be wherever so I have this thing centered at 0. This would be my null distribution. What I do for this thing right here, I take my z-score. So maybe my z-score is here. Zn, this is maybe 1.96. And I would have considered the more extreme values as well. I would compute that tail probability over here. And I would correspondingly compute that tail probability too, because it's the same distance away from theta naught. So I compute these tail probabilities, and that would be my p-value. It would be the sum of those two things. And it'd be equivalent to checking if this test statistic was less than 1.96. So if it was exactly 1.96, I would have this threshold right here, and I'd get a corresponding p-value of 0.05. So make sure you can go back and forth between those two things in your head. So they're all just one-to-one mappings of the exact same thing. Okay. So what did I say? This thing is not a measure of the null hypothesis. So what is it doing? It's calibrating error rate. So if I reject if this thing is less than 1.96, or equivalently if the p-value is less than 0.05, they're exactly the same thing, and I'll repeat the process. I go collect n more data points. I do this over and over and over again, so I collect n more data points, I compute this thing again, I check to see if it's less than 1.96. I repeat this over and over and over again. If theta naught was true, I would be rejecting the null hypothesis 5% of the time. So the p-value itself doesn't mean anything. I mean, Eric has the correct interpretation, that is what it means, but what does that mean? More extreme data, I don't know what it means. Data you never saw that was unlikely to occur in the first place, what does that mean? I don't know. So, what is it in terms of a frequentist process? It's saying if the null were true, and you repeat this over and over again, you will reject incorrectly 5% of the null hypothesis. That's what Neyman and Pearson are doing for you. You might ask about the other error rate. The test statistic they gave you was the one that minimized that error rate. That's what the Neyman Pearson proof is all about. I don't cover that here, but I do cover it in the spring. Any questions about all that? Sound like what you learned before? Maybe? They may have just taught you a process and just said you do it. Okay. So I said p-values are not evidence of the null. So let's consider two different types of hypotheses. Two differing hypotheses. Okay, one of them looks like this. H naught theta is equal to theta naught. H alpha theta is not equal to theta naught. Or, here's the other one. So this one's called the Sharp test. Or the point null test, or the simple versus composite test. Lots of names for the exact same thing. Or this test. Theta is greater or equal to theta naught. An alternative is going to be theta less than theta naught. This is the one-sided test. Let's say you came up with a p-value of 0.05. I haven't told you which test we're computing, so let's imagine I'm computing the Sharp test. So say, under the Sharp test, we compute .05. Now this might baffle you. You've never seen a p-value of 0.05 in your life. I guarantee you've never computed one on a real problem that actually turned out 0.05. So if it did, what would you do? I don't know. So let's make your life easy. Minus epsilon. So it's 0.499999999. Is that strong evidence against the null hypothesis? Under the current paradigm, people say yes. So I'm going to try to change your mind on that and say that's actually pretty weak evidence. Will take a few days to get there. So let's say I computed this, but we can think about 0.05 if you'd like. Let's just round that 0.05, but we know it's a number that's just slightly less. So say under the Sharp test, we compute this. So what we've computed is Zn. And we've computed xn bar minus theta naught over sigma over root n. So this is the number that we computed. So we computed something that's very close to 1.96 to come up with this. So this was 1.96. Is it a little bit bigger than 1.96 or is it a little bit smaller than 1.96? Bigger. Slightly bigger. So it's a whisker bigger. It's not epsilon, it's some other number. It's also very small. It maps to that. So epsilon prime. So you could say is equal to 1.96 plus epsilon prime, some other tiny number on different scales. So again, just think about this. We've been indoctrinated to think about those numbers as special. So the question is what does this mean in general? Let's think about as n gets big. So as n gets really big in all of this, let's think about if we would change our minds as to what this meant. So if n was small and we saw this, we might think, that's strong evidence. Let's think about it as n gets big. So as n goes to infinity, we know what this does, sigma over root n. So again, this doesn't happen in real problems. I'm just trying to say conditional on you thinking about this number, i.e. you thinking about this number, let's think about it as what it would mean as a function of n. So for a real problem, if we cranked up n, it wouldn't stay fixed at 1.96. It either drift away, it would drift away from it somehow. If the null were true, we'd flutter around it uniformly. If the alternative was true, it would dive down towards 0. So, but if this was fixed, and we thought about this as n, we know what that does. That goes to 0. So what does x bar do? X bar n goes to theta. So this is the law of large numbers. Weak law, strong law, it converges in any sense you want to think about it. So it's almost surely converging. So to that. But it goes to the truth. So that's the truth. But if this was going to be 1.96 in the limit, is I made this n go to infinity, and we know that's 0, what does this have to be going to? If you know what a derivative is, you know the answer to this. Derivatives are just rates of things that are both going to 0. It's the ratio of things that are going to 0. Unless one of them goes off to infinity and they triple. So what does the numerator go to? It goes to 0. So if this is going to be fixed at something, that's what a derivative does. It's this infinitesimal thing. So this is going to 0 as well if this is 1.96. What's the interpretation? This went to this 1.96 faster than that. 1.96 times faster, this went to 0 than that. That's what that means. So we also know that x bar n is going to theta naught, because this thing is 0 if this is fixed at 1.96. So what does that mean? Theta is equal to theta naught. So that goes to the truth. That goes to theta naught. So if this is, if you have a p-value of 0.05 and n is huge, then it means that theta is really close to theta naught. So you might say, hey, look, it's still a standard error wave. So it's still the standard error wave, and I can tell the difference between those two things. So I can measure epsilon. But on my scale, I might be thinking theta is awfully close to theta naught. That's the difference between practical significance and significant. Practical and statistical significance. So again, somebody tells me they have a p-value of 0.05, and they tell me n is super high, then I'm going to think theta is probably theta naught. Any discrepancy is probably because of your modeling assumptions. So might not be your hypothesis at all. If you did the one-sided hypothesis, what p-value would you have calculated? Anybody that's had a Stat 101 class can do this conversion real quickly. What's the one-sided p-value? What is it? .025, you have it. So you're just taking one of the tail sides. You'd be taking the left tail side if you're testing that. Chase the alternative direction. So one-sided p-value, one-sided case gives p-value very close to 0.025. It's the half of the other p-value. So if you're looking for a half p-value, if you have a 0.06 and you want it to be a 0.03, change your hypothesis direction real quickly. That would be considered extremely unethical to do that. So, but I see people do that kind of nonsense all the time. So, but it'd be about 0.025. I just have to have this little epsilon distance as well. This epsilon distance, not that one. Let's think about the sets that were just measured. If p-values were a measure of the null hypothesis, how big is this set? It's a point. It's tiny. Think about this set right here. How big is that? It's huge. So if the p-value was measuring what was more correct in general, and it was a measure, then a set that was bigger, that contained exactly the same point, should be getting bigger as I increase the hypothesis space. And it's not doing that. I will tell you, for a Bayesian test, they're all additive. And so they are measures. So this example alone, if you'd been thinking about p-values from the get-go, you would already know from this example, moving from a one-sided test to a point null test, that the p-value gets bigger when I collapse the size of the space to a point. It doesn't make a lot of sense. So p-values are not measures of null hypotheses, they calibrate errors. Bayesian posterior probabilities are measures of hypotheses. So we'll come back next time, do that Bayes factor calculation, show you the correspondence between a Bayes factor and the posterior probability. And if you want to know more about this Neyman Pearsonian stuff, take inference class. Make sure you've taken a formal probability class before you take inference class. Plus it's going to be excruciatingly hard. It's harder than this class. So anyway, but if you want to know all that mathematical nuance that I'm glossing over, I teach it in this way. That's it for now. We'll come back and keep adding to this conversation.